The Energy Frontier Research Center, or EFRC, at the University of Texas at Austin is one of 46 funded by the US Department of Energy. The EFRC here investigates fundamental chemical and physical processes that control how sunlight is converted to electricity in solar cells and how energy is used and stored in batteries for electric vehicles.
We need to move away from fossil fuel. But the problem is, how can we harvest sunlight efficiently on the economic scale, which competes with fossil fuel? That is a big problem. So we need the newest materials to do that, the newest theory to do that, and the new understandings. We really have a whole range of scientists with different expertise, from theory, from the measurements, from the physical aspect, from synthetic. And we also have world-class facilities here. There's a long tradition here of doing energy research.
The thing that excites me most is the fact that we have been very fortunate assembling a team in which every single member is collaborative in their nature. That's what they like to do. At this stage of development of science, you really can't do this kind of work without a big theoretical component. But it has to be a theoretical component that wants to understand the experiments. All of our theorists are exactly that type. We also have a very diverse group of theorists. A polymer expert, an electronic structure on surfaces expert, my own condensed phase and electronic dynamics expertise. And we all interact quite effectively, but we bring different specializations to the table.
Professor Goodenough has been called the father of the lithium-ion battery. Approaching 90, he is still as excited about technological developments as any researcher in the EFRC.
In the EFRC program, we're working on primarily cathode materials for the lithium-ion battery. One would like to go to higher voltages, higher capacity, and higher energy density. We make the materials. We identify a particular problem that we're interested in from an engineering point of view, and then we take advantage of the techniques that are available over in chemistry, both theoretical and experimental. They have spectroscopic techniques, they have SIMS techniques, and so on for being able to do characterization and analysis of materials. We essentially bring the problem, and they help us very much in the analysis of the problem.
We have to deal with how does charge transfer between multiple interfaces? What are the structures of those interfaces? How do these interfaces interact with each other? It's a very complex problem. We need physical chemists, we need theoreticians, we need engineers, we need synthetic chemists, all working together to tackle this problem from multiple different angles. There's a synergy between all of that. There's overlap in expertise, and together, the sum is basically greater than the parts. So our main goal is to come up with molecules and materials that help us address the most important problems that are limiting those devices from reaching broader applications.
The centre is developing strong collaborations with industry to further its research in plastic solar cells.
Karalee is this company producing something called power plastic. The advantage of power plastic is that it can be produced on a very large scale, and it's very lightweight. So you can roll out a solar panel so easy, and you can put it on the building. The limitation right now is the efficiency. It's nowhere near silicon solar cells. Karalee has worked on this problem for quite a few years. They have a huge library of materials. Some materials fail spectacularly. From an industrial point of view, you should just toss it away. But for us, it's actually great. Let's figure out why it fails spectacularly, right? Then we can figure out the mechanisms. So this is a big advantage for us. We're already getting very interesting materials from them to look into why this particular physical mechanism happens in this particular material.
The major challenge for us is finding materials that are going to be long-lasting, inexpensive, and safe for lithium-ion batteries. What I specifically do is that I'm working with other people who synthesize materials, and I look at them and I kind of get an idea of what's going on. And then I say, well, if we can tweak this about the material, then I can look at it and we can have an even greater understanding of how these materials are behaving while they're in the battery. Being a part of something that's so new and forthcoming, and knowing that I could be involved in something that's going to better my generation and future generation, and that's really cutting edge, and to be evolving with that process and to be able to, possibly come up with some material that's going to completely change our society, and we're going to be able to drive cars 500 miles without ever having to charge them and without putting carbon dioxide in the atmosphere. It's a big responsibility, but it's a fun responsibility. It's really exciting to me.